At this very moment, the fastest object ever created by humanity is tearing through space at roughly 430,000 miles per hour. At a speed this extreme, you could loop around the entire Earth in less than 4 minutes. And yet, even moving fast enough to be instantly destroyed by contact with anything solid, this spacecraft would still take more than 6,000 years to reach the nearest star. That single fact alone overturns almost everything we instinctively believe about space travel. What truly limits how far a human can travel in one lifetime is not technology, funding, or ambition. The real constraint is far deeper. It is a boundary embedded into the structure of reality itself. And yet, hidden within that same boundary is an astonishing loophole. One so radical that it could allow a person to reach galaxies millions of light years away, while aging only a few decades. If you want to understand how far a single human life can truly stretch across the universe, and if this kind of exploration speaks to you, consider liking and subscribing. It helps more than you might expect. Take a breath. Let's begin. The fastest object humanity has ever launched is currently racing through space at a speed that defies everyday intuition. The Parker Solar Probe, launched in 2018, has surpassed 430,000 miles per hour during its closest encounters with the Sun. At that velocity, it could cross the entire continental United States in less than 25 seconds. Blink twice while standing in New York, and it would already be beyond Los Angeles, streaking over the Pacific and closing in on Hawaii. This is not a small achievement. It represents the absolute peak of human engineering. Decades of research, billions of dollars, and the collective expertise of thousands of scientists and engineers all converged into this single machine. Rather than relying solely on raw engine power, the Parker Solar Probe uses a carefully choreographed sequence of gravitational assists from Venus. Each flyby siphons a minute amount of orbital energy from the planet, slowly stacking speed over years of precision adjustments. This is motion achieved through cosmic choreography, not brute force. It is humanity's fastest sprint into the void. To truly appreciate how extraordinary this is, it helps to step back and look at the full arc of human speed. For more than 200,000 years, the fastest any human could travel was around 25 miles per hour, the top speed of a galloping horse. That limit endured for nearly all of human history. By the dawn of the 20th century, automobiles pushed past 60 miles per hour. In 1903, the Wright brothers lifted off at just 34 miles per hour. 60 years later, pilots shattered the sound barrier at 761 miles per hour. In 1969, astronauts returning from the moon reached nearly 25,000 miles per hour, the fastest speed any human body has ever experienced. The Parker Solar Probe moves roughly 17,000 times faster than those Apollo astronauts. No human could survive on board. Not because of the velocity itself, but because the probe dives close enough to the Sun to endure temperatures exceeding 2,500 degrees Fahrenheit. This speed is the result of decades of gravitational finesse, not engines. And yet, even this staggering achievement exposes a brutal truth about our place in the universe. At 430,000 miles per hour, the Parker Solar Probe would need approximately 6,600 years to reach Proxima Centauri, the closest star beyond our Sun, just 4.24 light-years away. In human terms, that means a journey launched when the ancient Sumerians first etched symbols into clay tablets would only now be nearing its destination. A human life averages around 80 years. At humanity's absolute maximum speed, you would traverse barely more than 1% of the distance to the nearest star before your heart stopped beating. The numbers become even more unsettling when you calculate what a full human lifetime achieves at these record speeds. Traveling continuously for 80 years at the Parker Solar Probe's peak velocity would cover roughly 3 trillion miles. That number carries 12 zeros. It sounds immense, until it is placed against the true scale of the cosmos. 3 trillion miles equals about 0.05 light-years. The nearest star lies more than 80 times farther away than what an entire lifetime of non-stop travel could reach. You would spend your whole existence in motion and still remain trapped within your local stellar neighborhood. The Oort cloud offers another sobering benchmark. This vast spherical shell of ancient icy debris surrounds our solar system and marks the outermost reach of the Sun's gravitational influence. It stretches as far as 100,000 astronomical units from the Sun, with 1 astronomical unit being the distance from Earth to the Sun, about 93 million miles. The Oort cloud is the true frontier of our solar system, where the Sun's gravitational hold finally weakens and interstellar space genuinely begins. At humanity's current maximum speed, even reaching the inner edge of the Oort cloud would take roughly 600 years of continuous travel. A full human lifetime, even at unprecedented velocity, would not come close to escaping the Sun's gravitational domain. You would die long before leaving its extended family of orbiting debris. Measured against cosmic scales, your entire life of travel would amount to little more than crossing from Manhattan to Brooklyn. Voyager 1 provides a real-world illustration of what decades of space travel actually accomplish. This probe has traveled farther than any human-made object in history. After more than 47 years of non-stop motion through interplanetary, and now interstellar space, Voyager 1 has covered about 15 billion miles. It crossed the heliopause in 2012, the boundary where the Sun's solar wind finally yields to the pressure of interstellar space. Headlines declared that Voyager had left the solar system. That statement is technically correct, and deeply misleading. Voyager escaped the Sun's magnetic influence, but it remains firmly bound by the Sun's gravity. It will not pass beyond the Oort cloud for another 30,000 years. 15 billion miles sounds extraordinary, until you realize it represents less than 0.03% of the distance to the nearest star. If the journey to Proxima Centauri were scaled down to a road trip from New York to Los Angeles, about 2,800 miles, Voyager's entire 47-year journey would equal roughly 100 feet. You would still be standing in your driveway, barely past the mailbox, after half a century of continuous driving. Here is another way to feel the imbalance. Light travels at 186,000 miles per second. In the time it took you to read this sentence, light traveled far enough to circle Earth 7 times. Voyager 1's nearly 5-decade journey covers a distance that light crosses in about 20 hours. 47 years of human travel equals less than 1 day at light speed. The 4 light-year distance to Proxima Centauri is more than 150,000 times farther than Voyager has traveled so far. Voyager 1 moves at about 38,000 miles per hour relative to the Sun. Impressive by human standards, devastatingly slow by cosmic ones. At that speed, it would take over 70,000 years to reach Proxima Centauri. If it somehow survived the journey, the humans who launched it would have been extinct longer than our entire species has existed so far. Homo sapiens emerged around 300,000 years ago. Voyager would need nearly a quarter of that entire span just to reach our closest stellar neighbor, and it will never arrive. Voyager 1 depends on a plutonium-powered generator, whose output steadily declines as radioactive decay does its quiet work. Long before the spacecraft ever comes remotely close to another star, its instruments will go dark, leaving behind a drifting relic, a message cast into space by a civilization that will no longer be there to remember it. That power source loses roughly 4 watts of output every year as the plutonium slowly exhausts itself. By 2025, Voyager will no longer have enough energy to operate any of its scientific instruments. By 2036, it will fall completely silent. From that moment on, it will continue its voyage as an inert artifact, tumbling endlessly through interstellar space. For tens of thousands of years, it will wander without purpose, a mute monument to human ambition, never reaching a destination, never again witnessed by human eyes. The deeper obstacle is not endurance, but propulsion itself. Every rocket humanity has ever launched, without exception, relies on the same basic principle that propelled the first Chinese fireworks more than 1,000 years ago. Hot gas is expelled in one direction, forcing the vehicle to move in the opposite direction. Newton's third law made manifest. You throw mass backward, and the reaction pushes you forward. It is elegant. It is simple. And for interstellar travel, it is catastrophically inadequate. Chemical propulsion is trapped by a hard boundary defined by the Tsiolkovsky rocket equation. First formulated in 1903 by Russian scientist Konstantin Tsiolkovsky, this equation dictates the maximum speed a rocket can ever achieve based on just 2 variables. One is exhaust velocity, how fast the propellant is expelled from the engine. The other is the mass ratio, the rocket's total mass when fully fueled compared to its mass after the fuel is gone. For chemical rockets, exhaust velocity tops out at around 4.5 kilometers per second. This is not a technical shortcoming waiting for a breakthrough. It is a fundamental limit imposed by chemistry itself. When hydrogen and oxygen burn, the most energetic chemical reaction practical for rocketry, the resulting water molecules can only move so fast. The energy released by rearranging chemical bonds has an absolute ceiling. No refinement, no ingenuity, no clever engineering can force those molecules to exit a nozzle faster than the laws of chemistry allow. The brutality of the rocket equation becomes undeniable when you ask what it would take to reach even modest interstellar speeds using chemical propulsion. To accelerate a probe weighing just 1,000 kilograms to 1% of the speed of light would require an initial fuel mass greater than the mass of the observable universe. Not the Earth, not the Sun. Not all the stars in the Milky Way combined. Every galaxy, every star, every planet, every atom across the entire visible cosmos would still not supply enough chemical fuel to push a small car to 1% light speed. This is not rhetorical exaggeration. It is the literal outcome of the mathematics. The rocket equation contains an exponential term that mercilessly punishes attempts to reach high velocities. Each additional increment of speed demands not just more fuel, but exponentially more fuel. The curve rises so violently that it rapidly surpasses any physically meaningful quantity of matter. Gravity assists offer partial relief from this constraint. Instead of burning fuel, spacecraft can steal energy from planets through carefully planned flybys. By approaching a massive body at just the right angle, a spacecraft can exchange momentum with the planet, incrementally increasing its speed through gravitational interaction. The Voyager probes relied heavily on this technique, slingshotting from Jupiter to Saturn, to accumulate the velocity that carried them toward interstellar space. The Parker Solar Probe uses repeated Venus flybys to reach its record-breaking speeds near the Sun. The physics of gravity assists are deceptively simple. A spacecraft falls toward a planet, accelerates under its gravity, and departs along a trajectory that converts a fraction of the planet's orbital momentum into spacecraft speed. The planet loses an immeasurably tiny amount of energy. The spacecraft gains thousands of miles per hour. After each Voyager flyby, Jupiter moves ever so slightly slower in its orbit, a change far too small to detect. But gravity assists are not a loophole to the stars. The solar system contains only a limited number of massive bodies positioned in useful configurations. Jupiter is our most valuable gravitational resource, and even it can only give so much. Each boost costs years of travel time to reach the next encounter. The same orbital mechanics that enable gravity assists also impose strict limits on how much total energy can be extracted from the planets. A spacecraft designed exclusively to maximize gravitational boosts, bouncing between planets over decades of meticulous planning, might eventually reach speeds approaching 150,000 miles per hour. That is roughly 4 times Voyager's current velocity. An extraordinary achievement by engineering standards, and still utterly useless for interstellar travel on any human timescale. At that speed, the nearest stars remain tens of thousands of years away. The fastest spacecraft ever sent outward from the Sun using gravity assists is New Horizons. After receiving a powerful boost from Jupiter in 2007, it raced past Pluto in 2015 at about 36,000 miles per hour relative to the Sun. It was moving faster than any previous outbound probe. The images it transmitted back revealed a world of unexpected complexity. Nitrogen glaciers, towering mountains of water ice, a landscape far more dynamic than anyone had imagined. And yet, even at that velocity, New Horizons would require more than 80,000 years to reach Proxima Centauri. Ion propulsion systems improve efficiency by dramatically increasing exhaust velocity. Instead of expelling hot gas, these engines ionize a propellant, usually xenon, and accelerate the charged particles using electric fields. The ions exit the engine at speeds 10 to 20 times greater than chemical exhaust, allowing much more effective use of propellant mass. The Dawn spacecraft used ion propulsion to explore the asteroid belt, becoming the first mission to orbit 2 separate bodies beyond Earth. Its engines allowed gradual but profound changes in trajectory over months of continuous thrust. maneuvers that would have been impossible with chemical rockets of comparable mass. But efficiency comes at a cost. Ion engines trade power for patience. Their thrust is so faint it borders on the imperceptible. Dawn's ion drive produced only about 90 millinewtons of force. To understand how little that is, rest a single sheet of paper flat on your open hand. The downward pressure of that paper is roughly equivalent to the push generated by an ion engine. Applied continuously, year after year, that tiny force can indeed build speed. But it does so on timescales measured in decades, not seconds. Chemical rockets burn furiously for minutes or hours. Ion engines whisper for years. Even with unlimited fuel and a full century of uninterrupted operation, ion propulsion cannot approach the velocities required to make interstellar travel practical within a human lifetime. You could run an ion engine for every year of your life and still fall far short of the speeds needed to significantly shorten journeys to nearby stars. Ion propulsion excels at delicate, efficient maneuvering within our solar system. It offers no escape from the tyranny of interstellar distance. Ion engines are extraordinary at what they do, but what they do is not enough. Nuclear thermal rockets climb one rung higher on the propulsion ladder. Instead of relying on chemical reactions, these engines pass hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before expelling it through a nozzle. Because nuclear energy is vastly more potent than chemical combustion, the hydrogen can be ejected at nearly twice the exhaust velocity of conventional rockets. That single improvement dramatically softens the rocket equation's cruelty. NASA explored this concept extensively during the NERVA program throughout the 1960s and early 1970s. Engineers conducted dozens of successful ground tests, running nuclear reactors at full power for extended periods, and demonstrating that nuclear thermal propulsion was not speculative. It worked. The technology was mature enough for flight before political priorities and budget pressures shut the program down in 1973. Humanity has known how to build nuclear rockets for more than half a century. We simply chose not to. A nuclear thermal rocket could, in theory, accelerate a spacecraft to around 100,000 miles per hour with reasonable fuel ratios. That is a substantial improvement over chemical propulsion, roughly tripling achievable speeds. At that velocity, the travel time to Proxima Centauri would shrink to about 28,000 years. Still impossibly long for any individual human. Still longer than all of recorded human civilization. But progress nonetheless. Solar sails offer a more elegant idea. Instead of expelling mass, they harness the pressure of sunlight itself. When photons strike a reflective surface, they transfer momentum, exerting a gentle but continuous push. A sail that is large enough and light enough can use this pressure to accelerate without carrying any fuel at all. Japan's Ikaros spacecraft demonstrated this principle in 2010, successfully deploying a 14-meter sail and measuring acceleration produced solely by sunlight. The experiment proved that photon pressure is not just theoretical. Light can push matter through space. With sufficiently advanced materials, solar sails could exploit this effect indefinitely without burning a single gram of propellant. Near the sun, where radiation intensity is strongest, a solar sail could theoretically achieve accelerations approaching 1% of Earth's surface gravity. That sounds impressive, until you notice the catch. To maintain that acceleration, the sail must remain close to the sun, and the entire purpose of propulsion is to leave. As the sail moves outward, sunlight weakens rapidly. Radiation pressure decreases with the square of distance. Double your distance from the sun, and the available push drops to 1/4. What seems powerful near the sun fades into insignificance in the outer solar system and disappears entirely between the stars. A sail launched from an extremely close solar pass might reach speeds of several 100,000 miles per hour before radiation pressure becomes too weak to matter. At 500,000 miles per hour, about 100 times the Voyager's speed, and faster than any spacecraft ever flown, the journey to the nearest star would still take more than 5,000 years. A human lifetime at that speed would cover roughly 350 billion miles, or about 0.6 light years. You would make it roughly 1/7 of the way to Proxima Centauri before dying in the emptiness between stars. This is the brutal reality of current and near-term propulsion. The fastest velocities humanity has demonstrated, tested, or could plausibly build within the next century are still hopelessly insufficient. Chemical rockets are fundamentally constrained. Ion engines are too weak. Nuclear thermal propulsion helps, but not nearly enough. Solar sails cannot accelerate massive payloads to the required speeds. We remain effectively confined within a few light hours of Earth. This limitation weighed heavily on early scientific thinking. Many 20th century physicists concluded that interstellar travel by biological beings was simply impossible. The energy demands were overwhelming. The travel times defied practicality. Radiation exposure during multi-decade voyages would accumulate to lethal levels. The vast, empty gulfs between stars appeared almost intentionally hostile to life. Some scientists began to suspect the universe enforced a kind of cosmic quarantine. Intelligent species, no matter how advanced, would be trapped on their homeworlds by sheer distance alone. The speed of light formed an unbreakable wall. Communication across the stars might be possible through radio signals that took years or centuries to arrive. But physical travel? That seemed forbidden. No meetings, no handshakes, no footsteps on worlds orbiting other suns. Space and time themselves appeared to enforce the rule. And yet, buried within the very equations that seem to imprison humanity, lies a loophole so deep it reshapes everything we believe about distance, time, and the limits of exploration. That loophole was uncovered in 1905 by a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein, and he asked a deceptively simple question, one that would dismantle 3 centuries of assumptions about the universe. What would happen, Einstein wondered, if you could ride alongside a beam of light? What would you observe? How would time behave? What would space itself do? The conclusions shattered common sense. They showed that the barrier confining humanity to its small corner of the universe is far less rigid than it seems. Distance and time are not immutable backdrops. They are malleable. They stretch and compress depending on how fast you move through space. A clock carried aboard a rapidly moving spacecraft does not advance at the same rate as a clock left behind on Earth. A measuring rod held by a traveler racing through space does not retain the same length as an identical rod resting motionless. The universe distorts space and time in ways that turn the seemingly impossible into something merely difficult. But to grasp how far a human life could truly reach, we must abandon our everyday understanding of motion. We must enter a domain where clocks tick at different speeds depending on velocity, where distances shrink for fast-moving travelers, and where the 80-year limit imposed by human mortality becomes far more flexible than it appears. The universe often seems engineered to frustrate our dreams of exploration. Yet embedded within those same rules are hidden allowances, provisions that could allow a single human lifetime to span distances that today exist only in the images of our most powerful telescopes. The same physics that erects the light-speed barrier also supplies the mechanism that makes that barrier almost irrelevant to the traveler. What follows will permanently change how you think about speed, time, and the true limits of human exploration. The cosmic prison we appear trapped inside has a door, and physics itself holds the key. In 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper to the German physics journal Annalen der Physik. Its title was unremarkable, giving no hint of the upheaval contained within. The paper relied on little more than algebra. It cited almost no prior research. It was written by a man with no academic position, no laboratory, and no institutional backing. And yet, this single document would dismantle 3 centuries of assumptions about the universe and reveal that time itself bends in response to motion. Albert Einstein began with an idea so simple it sounded almost obvious. The speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. Whether you are standing still on Earth or racing through space at half the speed of light, you will always measure light traveling at exactly 186,282 miles per second. This is not a limitation of instruments or technology. It is built into the fabric of reality itself. From this single postulate, consequences emerged that defied intuition. If the speed of light must remain constant for everyone, then something else must adjust to preserve that rule. That something turned out to be time. Clocks aboard moving spacecraft tick more slowly than identical clocks at rest. This phenomenon, time dilation, sounded absurd when first proposed. How could time, the most universal quantity imaginable, flow at different rates simply because of motion. But the mathematics were unavoidable, and within a few decades, experiments confirmed exactly what Einstein had predicted. Time dilation is real. It is measurable, and it rewrites everything we thought we knew about the limits of travel across the cosmos. The relationship between velocity and time dilation follows a precise formulae. Einstein introduced a quantity physicists call gamma, also known as the Lorentz factor. Gamma tells you exactly how much time slows down at a given speed. It is calculated by dividing 1 by the square root of 1 minus the square of your velocity divided by the square of the speed of light. The equation may look abstract, but the numbers it produces determine the fate of interstellar travelers. At everyday speeds, gamma is effectively equal to 1. A car on the highway experiences time dilation so tiny that only the most sensitive atomic clocks can detect it. A passenger on a cross-country flight ages a few nanoseconds less than someone who stayed home. The effect exists, but it is meaningless for daily life. Everything changes as velocity approaches a significant fraction of light speed. At 50% of light speed, gamma rises to about 1.15. Time aboard the spacecraft runs roughly 15% slower than on Earth. 1 year on the ship corresponds to about 14 months back home. Interesting, but not transformative. At 90% of light speed, gamma climbs to roughly 2.3. For every year experienced by the traveler, 2 years and 4 months pass on Earth. A 50-year journey at this speed would see the traveler age 50 years, while Earth aged more than a century. They would return to find grandchildren elderly and great-grandchildren shaping society. At 99% of light speed, gamma jumps to about 7.1. The effect intensifies dramatically. 7 years pass on Earth for every year aboard the ship. A decade of ship time corresponds to 70 years back home. A 50-year journey spans more than 3.5 centuries of Earth history. You would depart one civilization and return to another entirely. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time, compressed into a single year for the traveler. A 50-year voyage would carry Earth forward more than a millennium. The Roman Empire fell less than 1600 years ago. A journey like this would cross time spans rivaling the rise and collapse of entire civilizations. As velocity creeps ever closer to light speed, the numbers escalate relentlessly. At 99.99%, gamma surpasses 70. At 99.999%, it exceeds 200. At 99.9%, it climbs beyond 700. Each additional 9 added to the velocity multiplies time dilation by roughly 3. The implications are staggering. These numbers completely transform the question of interstellar travel. Consider not the nearest star, but a more distant destination. Vega, one of the brightest stars in Earth's night sky, lies about 25 light-years away. At conventional spacecraft speeds, reaching Vega would take hundreds of thousands of years. No human could survive even a fraction of that journey. But at 99% of light speed, with gamma at 7.1, the picture changes entirely. From Earth's perspective, the trip still takes just over 25 years. Light speed remains light speed. But for the traveler, time dilation compresses the journey to about 3.5 years. You could travel to Vega, explore any planets orbiting that brilliant blue-white star, and return having aged only 7 years, while 25 passed on Earth. Increase the speed to 99.9% of light speed, and the numbers become almost surreal. With gamma at 22, that same 25-year journey shrinks to barely more than 1 year of subjective time. You could visit Vega and return before your second birthday aboard the ship. Earth would age 50 years during your round trip, while you aged only 2. Now, push the journey even farther. The Pleiades star cluster, that unmistakable spray of blue stars visible to the naked eye on winter nights, lies about 440 light-years from Earth. At ordinary spacecraft speeds, reaching the Pleiades would take millions of years. But at 99.9% of the speed of light, where the gamma factor exceeds 70, the experience changes completely. The subjective travel time drops to roughly 6 years. You could journey to one of the most mythologized regions of the night sky, explore multiple stellar systems within the cluster, and return having aged perhaps 15 years, while nearly 9 centuries passed on Earth. Now consider the heart of our own galaxy. the center of the Milky Way sits approximately 26,000 light-years away. There, a supermassive black hole containing 4 million times the mass of our Sun dominates its surroundings, encircled by dense star swarms and extreme physical environments unlike anything near Earth. At 99.999% of light speed, with a gamma factor exceeding 223, the subjective travel time falls to around 116 years. Still longer than a natural human lifespan, but suddenly within reach of a multi-generational crew, or travelers supported by life extension technologies that may emerge in the centuries ahead. Increase the speed further to 99.9999% of light speed, where gamma rises above 700, and the transformation becomes astonishing. The journey to the galactic center compresses to roughly 37 years of ship time. A traveler could depart Earth at age 25, travel to the supermassive black hole at the core of the Milky Way, conduct observations impossible from any distance closer to home, and arrive having aged to 62. Upon return, they would discover that more than 52,000 years had passed on Earth. Entire civilizations would have risen and vanished, yet the traveler would have lived a single, ordinary human lifespan. The Andromeda Galaxy represents the ultimate test of relativistic travel within what we might call the local universe. Located about 2.5 million light-years away, Andromeda is the nearest major galaxy to our own. Its trillion stars form a spiral even larger than the Milky Way, potentially hosting countless worlds, and perhaps other intelligences. No conventional propulsion system could ever bridge this distance within any meaningful time frame. And yet, at velocities where gamma reaches 1 million, achievable only at speeds so close to light that the difference becomes almost philosophical, the subjective journey time to Andromeda collapses to roughly 2.5 years. A traveler could cross the gulf between galaxies, explore an entirely separate island universe, and experience the voyage as shorter than a typical doctoral program. Earth, meanwhile, would age 2.5 million years. Human civilization would almost certainly be unrecognizable or extinct, but the traveler would have aged only a few years. These calculations reveal a profound truth encoded within Einstein's equations, but hidden from everyday intuition. The universe has not erected barriers to forbid cosmic exploration. Instead, time dilation provides a mechanism by which human consciousness could traverse distances that light itself requires millions of years to cross. The limitation is not physics, it is engineering. The equations allow interstellar, even intergalactic, travel within a human lifetime. We simply lack the means to reach the necessary velocities. But why do such velocities demand such staggering amounts of energy? The answer lies in another of Einstein's revolutionary insights, captured in the most famous equation in physics, E = LMX second is mc2. This equation tells us that mass and energy are not separate substances, but interchangeable forms of the same underlying reality. That equivalence carries severe consequences for anything attempting to move at relativistic speeds. As an object accelerates, it gains kinetic energy. At low speeds, this increase follows the familiar rules described by Isaac Newton. Double your speed, and your kinetic energy increases fourfold. The relationship is simple and imposes no fundamental limit, provided you have enough fuel. But as velocity approaches a significant fraction of the speed of light, the behavior changes. The energy required for further acceleration rises faster than Newton's equations predict. Much faster. The object begins to behave as though it has more mass than it did at rest. This phenomenon, often described as relativistic mass increase, grows dramatically as speed increases. At 50% of light speed, an object behaves as though it has about 15% more mass than its rest mass. The additional energy you supply no longer translates cleanly into speed. At 90% of light speed, the effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now yields only modest gains, as if the spacecraft had suddenly become enormously heavy. At 99% of light speed, the effective mass increases by a factor of 7. At 99.9%, it exceeds 22. Each incremental gain in speed demands not just more energy, but exponentially more energy. The same gamma factor that helps the traveler by slowing time now works against them by inflating inertia. This is why the speed of light represents an absolute barrier for any object with rest mass. As velocity approaches light speed, effective mass approaches infinity. Accelerating an infinite mass would require infinite energy, and infinite energy does not exist. You can add 9 after 9 to your speed, expressed as a percentage of light speed, getting ever closer, but you can never quite arrive. The limit is asymptotic. Even far below that ultimate boundary, the energy demands are breathtaking. Consider accelerating a modest probe with a mass of just 1,000 kilograms to 90% of light speed. The kinetic energy required exceeds 10 to the 19th joules, a number with 20 digits. That is equivalent to the total energy output of the Sun for roughly 2 seconds, or the entire energy consumption of human civilization for about 1 million years, concentrated into accelerating a single small spacecraft. Now consider a crude interstellar vessel capable of sustaining human life with a mass closer to 100,000 kilograms. The energy requirement scales accordingly. Accelerating such a ship to 90% of light speed would demand energy comparable to the Sun's total output over several minutes. This is not a technological inconvenience awaiting a clever workaround. It is a requirement imposed by the structure of space-time itself. And the problem doubles when you remember that travelers usually want to stop when they arrive. Decelerating from 90% of light speed requires exactly the same amount of energy as accelerating to it. A round trip doubles the cost. A journey to Vega and back at 90% of light speed would require 4 full acceleration phases, an energy expenditure exceeding the Sun's output over a quarter of an hour. These realities explain why relativistic travel remains theoretical, despite being well understood for more than a century. No propulsion system humanity has built, tested, or seriously proposed can deliver energy on these scales. Chemical rockets fall short by billions. Nuclear fission improves the situation, but remains hopelessly inadequate. Even nuclear fusion, the process that powers the stars, struggles to provide the energy density required for practical relativistic propulsion. Acceleration itself introduces further constraints. Humans can tolerate continuous acceleration at 1 Earth gravity indefinitely. At that level, the force feels like normal weight. Travelers can walk, eat, sleep, and live normally throughout the journey. Higher accelerations quickly become problematic. Sustained 2 gravity acceleration causes fatigue and health issues. 5 gravities can induce blackout. 10 gravities can be fatal. At 1 gravity of continuous acceleration, a spacecraft would reach 90% of light speed in roughly 11 months. During the first half of the journey, the ship accelerates toward its destination. At the midpoint, it flips orientation and begins decelerating at the same rate, arriving with 0 relative velocity after an equal period of braking. This constant acceleration profile fundamentally alters travel time calculations. Instead of accelerating briefly and then coasting, the ship spends the entire journey either speeding up or slowing down. For short distances, this approach is inefficient. For vast interstellar voyages, however, continuous acceleration actually minimizes total travel time by maintaining thrust rather than drifting at a fixed speed. And it is within this framework, where time stretches, distance compresses, and energy reshapes inertia, that the apparent limits of a human lifetime begin to unravel. Under constant acceleration of 1 Earth gravity, the numbers change quickly. After 1 year of acceleration, a spacecraft would reach roughly 77% of the speed of light. After 2 years, it would approach 97%. After 3 years, it would exceed 99%. Each additional year yields smaller gains in velocity as the speed of light draws closer, but time dilation offsets this slowdown. As acceleration becomes less effective, the traveler's subjective time compresses more dramatically. The journey shortens from the inside, even as it remains long from the outside. From this behavior emerges one of the most famous consequences of relativity, the twin paradox. It deserves careful attention because it reveals just how deeply time dilation reshapes human experience. Imagine 2 identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light years away at 90% of light speed. Bob stays behind on Earth. From Bob's perspective, Alice's outbound journey takes about 22 years. Her return takes another 22. Bob waits 44 years in total, aging from early adulthood into retirement while his twin is gone. From Alice's perspective, the story is entirely different. At 90% of light speed, the gamma factor is about 2.3. Each 22-year leg of the journey feels like only 9.5 years. Alice experiences 19 years of travel in total, while Bob experiences 44. When Alice returns, she is 19 years older than when she left. Bob is 44 years older. Twins born on the same day are now separated by a quarter century of biological age. Alice may show the first hints of gray hair, while Bob's hair has turned white. Alice may still be advancing her career. Bob may be preparing for retirement. This result initially disturbed critics of relativity. Motion, they argued, is relative. From Alice's point of view, wasn't Bob the one moving away and then returning? Why should Alice age less rather than Bob? The resolution lies in asymmetry. Alice's journey involved acceleration, changes in velocity during departure, turnaround, and return. Bob's did not. That asymmetry breaks the equivalence of their reference frames and determines which twin ages less. This is not a thought experiment confined to theory. It has been verified experimentally. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world aboard commercial aircraft, comparing them to identical clocks left on the ground. The airborne clocks gained roughly 270 nanoseconds relative to the stationary ones, exactly as relativity predicted. The effect was tiny because airplane speeds are tiny compared to light speed, but it was real, measurable, and confirmed predictions made more than half a century earlier. Time dilation creates stranger consequences than aging differences alone. Travelers could continue receiving information from Earth throughout their journey. News broadcasts, messages, and entertainment would still arrive, but they would arrive compressed. Years of Earth time could unfold over months of ship time. Travelers could watch children grow into adults, and adults grow old in accelerated playback. Communication in the opposite direction is less forgiving. Messages sent from the spacecraft would take years to reach Earth, and replies would take years to return. A traveler moving at 99% of light speed toward a star 100 light years away would experience the journey in about 14 years. But a message sent 1 year into the trip would take decades to reach Earth. Any reply would arrive long after the traveler had already reached their destination. The visual experience of relativistic travel would be equally disorienting. Light arriving from ahead of the spacecraft becomes blue-shifted. Its frequency increases due to the Doppler effect created by motion toward the source. Stars in front would shift from familiar colors to blue, then ultraviolet, and eventually into X-ray wavelengths. Constellations once visible to the naked eye would vanish into invisible radiation detectable only by instruments. Light from behind undergoes the opposite transformation. It becomes red-shifted. Wavelengths stretch, sliding from visible light into infrared, then radio frequencies, and finally beyond detection altogether. The universe behind the traveler fades into darkness. Relativistic aberration further distorts perception. Light arriving from the sides appears to swing forward, compressed into a narrowing cone in the direction of travel. At 90% of light speed, most of the visible universe collapses into a circle about 60 degrees wide ahead of the spacecraft. At 99%, that circle shrinks to roughly 16 degrees. At even higher speeds, nearly all visible light concentrates into a brilliant point directly ahead, while everything behind disappears into blackness. The interstellar medium introduces another growing danger. Space between stars is not empty. On average, each cubic centimeter contains about one hydrogen atom, along with traces of helium, heavier elements, and dust. At low speeds, this material is harmless. Spacecraft pass through it almost unnoticed. At relativistic speeds, it becomes lethal. Each hydrogen atom strikes the spacecraft with kinetic energy multiplied by the square of the gamma factor. At 90% of light speed, individual atoms impact with energies comparable to cosmic rays. At 99%, that energy increases by another factor of 20. The spacecraft's forward surfaces would endure a relentless barrage of high-energy particles capable of damaging electronics, eroding materials, and penetrating living tissue. Shielding against this radiation presents severe challenges. Massive physical shields add weight that must itself be accelerated to relativistic speeds, increasing energy demands. Magnetic fields could deflect charged particles. but the required field strengths grow rapidly with velocity. Every solution compounds another problem. Despite these challenges, the underlying physics remains firm. Time dilation is not speculative. It is measured, tested, and confirmed by decades of experiments. The equations allow human travel across interstellar, even intergalactic, distances within a single biological lifetime. The obstacle is not physics, it is propulsion. So, what technologies could realistically reach the velocities required to exploit time dilation? What engines could deliver the staggering energy relativistic travel demands? The next chapter confronts that question directly, exploring propulsion concepts that attempt to bridge the gap between mathematical possibility and engineering reality. From nuclear explosions to antimatter annihilation to beams of light pushing ultra-thin sails across the void. The gulf between current spacecraft speeds and those required for meaningful relativistic travel is almost beyond comprehension. Our fastest probes move at roughly 1/10,000th of light speed. Noticeable time dilation begins only above 10% of light speed. Truly transformative effects appear only beyond 90%. Bridging that gap requires more than incremental improvement. It demands a revolution. The Parker Solar Probe reaches about 0.06% of light speed at its fastest. Reaching 10% requires increasing velocity by a factor of roughly 170. Reaching 90% requires multiplying our current maximum speed by about 1,500. This is not an engineering tweak. It is a leap across 6 orders of magnitude. And yet, humanity has conceived propulsion concepts that might cross this chasm. Some rely only on known physics and extraordinary engineering. Others demand advances in materials, energy production, or entirely new technologies. A few venture into speculative territory where the physics itself remains uncertain. Understanding these ideas reveals both the promise and the limits of interstellar travel within a human lifetime. Among the most audacious propulsion concepts ever examined by serious engineers is nuclear pulse propulsion. The idea took shape in the late 1950s at a laboratory in San Diego, when a small group of physicists posed a question that sounded borderline insane at first hearing. What if nuclear explosions could be used as a propulsion system? What if, instead of confining nuclear energy inside a reactor, you simply detonated bombs behind a spacecraft and let the blast waves push it forward through space? That proposal became known as Project Orion, and it attracted some of the sharpest scientific minds of the era. Freeman Dyson, Theodore Taylor, and dozens of other physicists and engineers devoted years to turning this outrageous idea into a concrete engineering design. These were not fantasists indulging in science fiction. They were disciplined scientists running calculations, building hardware, and testing real systems. The Orion concept was brutally straightforward. The spacecraft would carry a large inventory of nuclear explosive devices, essentially specialized bombs designed for propulsion rather than destruction. These devices would be ejected from the rear of the ship one at a time and detonated at precisely controlled distances. Each detonation would generate a rapidly expanding plasma fireball. A massive steel pusher plate mounted at the back of the spacecraft would intercept a portion of that plasma, absorbing its momentum and translating it into forward motion. Between the pusher plate and the crew compartment sat a system of enormous shock absorbers. Their role was to transform the violent, instantaneous impulses from each explosion into a smoother, survivable acceleration that humans and onboard systems could tolerate. The Orion team did not leave this idea on paper. They conducted physical experiments using conventional chemical explosives instead of nuclear devices. Small-scale models equipped with pusher plates were built and tested. Charges were detonated beneath them. The results were unambiguous. The models lifted off. The plates survived repeated blasts. The shock absorption systems performed exactly as intended. The program was halted in 1963, not because the concept failed, but because nuclear test ban treaties made atmospheric and space-based nuclear detonations politically unacceptable. Atomic devices were never tested in flight, but the underlying physics had already been demonstrated. Performance estimates showed that Orion could surpass every propulsion system conceived before it, and most proposed since. A relatively modest Orion craft using fission-based nuclear devices could reach velocities on the order of 3 to 4% of light speed. Larger designs employing hydrogen fusion explosives could potentially achieve 8 to 10% of light speed. The most ambitious versions, requiring engineering capabilities beyond those available in the 1960s, might push toward 15% or more. At 10% of light speed, a journey to Tau Ceti, a sun-like star about 12 light-years away that may host potentially habitable planets, would take roughly 120 years, still longer than a single human lifetime, but within reach of multi-generational missions, or travelers willing to spend most of their lives in transit. Time dilation at this speed offers little relief, compressing the journey by only about 0.5%. The ship's crew would experience nearly the same duration as observers on Earth. The engineering challenges of nuclear pulse propulsion are severe, but not impossible. The pusher plate must endure repeated exposure to nuclear fireballs. Temperatures of millions of degrees delivered in microsecond pulses, thousands of times over the course of the journey. Advances in materials science since the 1960s suggest that modern composites, ablative coatings, and refractory metals could potentially survive such punishment. The shock absorption system must reliably convert explosive impulses into steady acceleration without destroying the spacecraft or killing its occupants. This problem appears solvable with sufficient engineering rigor. The most obvious risks involve safety. Carrying thousands of nuclear devices introduces grave dangers during launch and throughout the mission. A catastrophic failure during Earth departure could scatter radioactive material across large regions. An accident during flight could terminate the mission instantly. Even so, nuclear pulse propulsion requires no new physics and no exotic materials beyond human capability. It represents one of the most plausible near-term paths to interstellar velocities using concepts we already understand. In the late 1980s, a related idea resurfaced in the form of Project Longshot, a study conducted by the United States Naval Academy between 1987 and 1988. Longshot examined a fusion-powered variant of nuclear pulse propulsion. Instead of fission bombs, the design relied on small fusion detonations, improving efficiency while reducing radioactive contamination. The Longshot concept aimed to reach Barnard's star, approximately 6 light-years away, in about 100 years at speeds near 4.5% of light speed. The study concluded that such a mission was technically feasible using technology that could be developed within a few decades. Antimatter propulsion occupies a different category entirely. It offers energy densities that dwarf every other known fuel source, while remaining grounded in well-established physics. When matter encounters antimatter, both annihilate completely, converting 100% of their combined mass into energy. By comparison, nuclear fission converts about 0.1% of mass into energy, and nuclear fusion converts roughly 0.7%. Antimatter is therefore about 140 times more energy dense than fusion, and roughly 1,000 times more efficient than fission. A single gram of antimatter annihilating with 1 gram of ordinary matter releases approximately 180 trillion joules of energy, comparable to the explosive yield of the Hiroshima atomic bomb. That amount of energy equals the electricity consumption of an average American household for more than 4 years. Directed properly, it could accelerate a spacecraft to velocities utterly unattainable by chemical propulsion, regardless of fuel supply. An antimatter rocket would operate by channeling the products of matter-antimatter annihilation through a magnetic nozzle to generate thrust. When an electron meets a positron, both vanish, producing gamma rays. When a proton meets an antiproton, the annihilation produces a cascade of particles known as pions. These charged particles can be guided magnetically, and as they decay into muons and then electrons, additional thrust can be extracted. The effective exhaust velocity of an antimatter engine approaches a significant fraction of light speed itself. This radically alters the rocket equation that cripples chemical and nuclear propulsion. With antimatter, relativistic spacecraft velocities become mathematically plausible rather than absurd. Consider a mission to Epsilon Eridani, a young sun-like star roughly 10 to 12 light-years away that hosts at least one confirmed planet. At 30% of light speed, achievable in theory with about 100 kilograms of antimatter for a modest probe, the journey would take roughly 35 years as measured from Earth. Time dilation compresses the traveler's experience to about 33 years. A human could depart at age 30 and arrive at Epsilon Eridani at a subjective age of 63, still potentially capable of exploration. Increasing antimatter supply allows higher velocities and stronger relativistic effects. With several thousand kilograms of antimatter, a crude interstellar vessel could theoretically reach 70 or 80% of light speed. At those velocities, the same journey would take about 13 to 14 years from Earth's perspective, while the travelers would experience only 8 or 9 years. What once demanded most of a lifetime becomes a demanding but feasible expedition. The true barrier to antimatter propulsion is not physics, but production. Antimatter does not exist naturally in usable quantities anywhere in the known universe. Every antiproton must be manufactured in particle accelerators through collisions that consume enormous amounts of energy. Current global antimatter production amounts to perhaps 10 to 20 nanograms per year, generated primarily at facilities such as CERN in Switzerland and Fermilab in the United States. To put this into perspective, accumulating 100 kilograms of antimatter at today's production rates would require roughly 5 billion years. The energy cost compounds the problem. Producing antimatter through accelerator collisions consumes on the order of 10 billion times more energy than the antimatter ultimately contains. Manufacturing enough antimatter for even a single interstellar probe would require energy inputs exceeding total human civilization's output for centuries or millennia. Storage presents another nearly insurmountable challenge. Antimatter annihilates instantly upon contact with normal matter, requiring containment systems that suspend it in perfect vacuum using magnetic fields. The fuel must never touch the container walls, must remain stable during launch vibrations, and must survive decades of storage during interstellar flight. The longest period antimatter has ever been stored successfully is on the order of 16 hours, achieved at CERN in 2023. Extending that window from hours to decades would require an improvement of roughly 4 orders of magnitude, a leap so vast that it remains far beyond any current or foreseeable capability. These twin obstacles of production and storage push antimatter propulsion firmly into the realm of the distant future, if it ever becomes practical at all. The physics is elegant and uncompromisingly sound. The engineering, however, lies far beyond anything humanity can plausibly achieve in the near term. Antimatter stands as a theoretical benchmark, the gold standard against which other propulsion ideas are measured, but not as a realistic pathway to the stars anytime soon. Beamed energy propulsion avoids the central flaw shared by every rocket-based system. Rockets must carry their energy source with them, and that energy source has mass. That mass must be accelerated, which demands more fuel, which adds more mass, creating a self-defeating cycle. Beamed propulsion breaks this loop by keeping the power source at home. The concept dates back to the 1960s, when physicist Robert Forward proposed using powerful lasers to accelerate extremely lightweight sails to interstellar speeds. A sail carries no propellant. It gains momentum purely by reflecting photons. With lasers powerful enough and sails light enough, velocities approaching significant fractions of the speed of light become theoretically possible. The most serious modern effort to pursue this idea is Breakthrough Starshot, announced in 2016, with an initial $100 million investment from Yuri Milner. The project, publicly endorsed by Stephen Hawking before his death, proposes using a massive ground-based laser array to propel tiny spacecraft, called starships, to about 20% of the speed of light. At that velocity, a journey to the Alpha Centauri system would take roughly 20 years. The Starshot concept envisions a phased laser array with a combined output approaching 100 gigawatts, comparable to the electrical output of about 100 large nuclear power plants. This beam would be focused on a spacecraft weighing only a few grams. The vehicle would consist of a reflective sail roughly 4 meters across, attached to a microchip containing cameras, navigation systems, and communication hardware. Under the pressure of this concentrated light, the sail would accelerate from rest to 20% of light speed in about 10 minutes. The engineering challenges are extreme, but not obviously impossible. The laser array must maintain precise focus on a rapidly accelerating target, as light travel delays stretch from milliseconds to seconds, and eventually minutes. The sail must survive radiation intensities capable of vaporizing ordinary materials, requiring advanced reflective coatings that remain largely theoretical. The Starship itself must function as a complete scientific spacecraft while weighing less than a paperclip. Despite these hurdles, beamed propulsion offers real advantages. The laser array stays on Earth, where it can draw power from terrestrial infrastructure, be repaired, upgraded, and reused. Each individual probe is relatively inexpensive, allowing hundreds or thousands to be launched. Even if many fail, the odds improve that at least some will survive long enough to transmit valuable data. For robotic exploration, this approach may be sufficient. For human travel, however, it encounters a fatal limitation: deceleration. A laser-driven sail accelerates by being pushed from behind. Once it reaches its destination, there is no laser waiting there to slow it down. A Starshot probe would scream through the Alpha Centauri system at 20% of light speed, with only minutes to observe before it vanished forever into interstellar space. That may be acceptable for flyby photography. It is utterly inadequate for travelers who wish to stop. Magnetic sails offer one possible solution to this breaking problem. A superconducting loop can generate an enormous magnetic field that interacts with charged particles in the interstellar medium or the stellar wind of the destination star. This interaction produces drag, gradually bleeding off the spacecraft's kinetic energy. In principle, a magnetic sail could decelerate a relativistic spacecraft to rest over months or years. In practice, the challenges are formidable. Slowing from 20% of light speed requires dissipating colossal amounts of energy, heating the magnetic structure and nearby components. Superconducting loops must retain their properties under intense thermal stress, demanding extremely advanced cooling systems. The density of the interstellar medium also varies unpredictably, complicating deceleration profiles and control. Fusion propulsion may represent the most realistic route to velocities where time dilation becomes meaningful for human travelers. Fusion reactions combine light atomic nuclei, usually hydrogen isotopes, releasing energy vastly exceeding that of chemical or fission reactions. The Sun itself is powered by fusion, converting hydrogen into helium and flooding space with energy. The physics of fusion propulsion is well understood. When deuterium and tritium fuse, they form helium and a high-energy neutron, releasing about 17.6 million electron volts of energy per reaction, millions of times more than chemical processes. A fusion rocket could theoretically achieve exhaust velocities of 3 to 5% of light speed, allowing spacecraft to accelerate to 10 or even 15% of light speed with manageable fuel ratios. The most detailed fusion-based interstellar design remains Project Daedalus, developed by the British Interplanetary Society between 1973 and 1978. The Daedalus spacecraft was conceived as a two-stage fusion-powered probe, burning pellets of deuterium and helium-3 via inertial confinement fusion. Electron beams would compress each pellet until fusion ignited, ejecting reaction products through a magnetic nozzle to produce thrust. Daedalus was designed to reach Barnard's star, about 6 light-years away, in roughly 50 years, cruising at 12% of light speed. The first stage would burn for 2 years, accelerating the craft to 7.1% of light speed before detaching. The second stage would fire for another 1.8 years, pushing the spacecraft to its final velocity before coasting the remaining distance. The spacecraft would be enormous by any standard, with a launch mass around 54,000 tons, almost all of it fuel. It carried no deceleration system. Instead, it would rush through the Barnard's star system at relativistic speed, collecting data during a brief flyby before continuing into interstellar space forever. Project Icarus, launched in 2009 by the British Interplanetary Society and the Tau Zero Foundation, revisited the Daedalus concept using updated assumptions. Icarus studies examined alternative fusion fuels and engine configurations, generally confirming that velocities between 10 and 20% of light speed might be achievable with fusion technology developed within the next century. At 15% of light speed, a journey to Sirius, the brightest star in Earth's night sky, about 8.6 light-years away, would take roughly 57 years from Earth's perspective. Time dilation at this speed reduces the traveler's experience by only about 1%. A person leaving Earth at age 25 would arrive at age 82, having spent nearly their entire adult life in transit. Survival, perhaps, but not a practical mode of exploration. Achieving velocities where time dilation provides dramatic benefits requires propulsion beyond conventional fusion. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, offered an elegant theoretical solution. Instead of carrying fuel, the spacecraft would scoop hydrogen directly from the interstellar medium, using vast magnetic fields, fusing this collected material to generate continuous thrust. In theory, such a craft could accelerate indefinitely, limited only by relativistic effects as it approached light speed. The idea captivated both scientists and science fiction writers for decades. It seemed to promise true relativistic travel without the crushing fuel mass penalties of rockets. Detailed analysis eventually exposed fatal flaws. The interstellar medium contains, on average, only about 1 hydrogen atom per cubic centimeter, far less in many regions. To collect enough fuel, a magnetic scoop thousands of kilometers across would be required. That scoop, however, interacts with incoming particles, generating drag greater than the thrust produced by fusion. The ramjet becomes a cosmic parachute. Later studies suggested the concept might function in unusually dense environments, such as molecular clouds, but fails in typical interstellar space. Unlimited acceleration through fuel harvesting appears impossible under known physics. Hybrid propulsion systems may offer the best compromise. A spacecraft might use nuclear pulse propulsion to reach initial speed, then deploy a magnetic sail to brake at its destination. Alternatively, a laser array could provide early acceleration, while an onboard fusion engine handles deceleration and maneuvering upon arrival. Now imagine a hybrid mission to the Tau Ceti system, 12 light-years from Earth and home to several planet candidates, some potentially capable of supporting life. In this scenario, the initial phase of acceleration does not come from onboard engines at all. Instead, a powerful ground-based laser array pushes against a reflective sail attached to a fusion-powered spacecraft. During the first weeks of the journey, the laser accelerates the vessel to roughly 15% of the speed of light. Once that velocity is reached, the sail is discarded, and the spacecraft enters a long coasting phase lasting approximately 80 years. Near its destination, the fusion drive ignites, providing the braking force needed to slow the vessel enough to enter orbit around Tau Ceti itself. This hybrid architecture offloads the energy-intensive acceleration phase to Earth while preserving onboard propulsion for deceleration, the crucial step that transforms a fleeting flyby into genuine exploration. The total travel time, roughly 80 years, still exceeds a natural human lifespan. But a crew departing in their 20s might plausibly survive to arrival in their late 90s or beyond, assuming continued advances in medicine and life extension technologies over the coming century. This is not comfortable travel. It is endurance. But it is no longer impossible. Beyond these approaches lie propulsion concepts that push into territory where physics becomes speculative or entirely hypothetical. Among the most famous is the Alcubierre warp drive, proposed in 1994 by physicist Miguel Alcubierre. The idea describes a configuration of spacetime that allows effective faster-than-light travel without violating special relativity. The mechanism is conceptually radical. Space is contracted in front of the spacecraft and expanded behind it, forming a bubble of flat spacetime that moves through the universe like a wave. Inside this bubble, the spacecraft remains stationary relative to its local spacetime. No speed limit is broken because the vessel itself is not moving through space. Space is being reshaped around it. In principle, destination's light would require years to reach could be accessed in arbitrarily short times, depending on how strongly spacetime is distorted. Mathematically, the Alcubierre solution is valid within general relativity. The equations describe a self-consistent, if exotic, geometry of spacetime. The obstacle lies in the requirements. Creating such a warp bubble demands negative energy density, a form of energy that may not exist in usable quantities in nature. Even the most optimistic estimates place the required energy on the order of the mass energy of Jupiter. More realistic calculations push the requirement beyond the mass energy of the entire observable universe. The warp drive remains elegant mathematics without any plausible path to physical realization. Wormholes offer another speculative shortcut. These hypothetical structures, permitted by general relativity, would connect distant regions of spacetime through tunnels that bypass normal three-dimensional distance. A traveler entering one mouth of a wormhole could emerge from the other light years, or even billions of light years away, having traversed effectively no distance at all. But traversable wormholes face severe theoretical challenges. They require exotic matter with negative energy density to remain open against gravitational collapse. While certain quantum effects suggest that small amounts of negative energy might exist, there is no evidence that such effects can be scaled to macroscopic levels. Even if stable wormholes could be created, their usefulness for exploration remains questionable. One mouth would still need to be transported to the destination through conventional space before a shortcut could exist, reintroducing the propulsion problem wormholes were meant to solve. Returning to technologies grounded firmly in known physics, the realistic frontier for interstellar travel likely rests with advanced fusion propulsion, potentially supplemented by beamed energy during the initial acceleration phase. With sustained research and development, such systems might reach velocities of 15 to 20% of light speed within the next century. At 20% of light speed, time dilation remains modest. The gamma factor is only about 1.0021. 50 years of Earth time compressed to roughly 49 years aboard the spacecraft. The traveler gains perhaps a single year. Noticeable, but far from transformative. True relativistic benefits do not emerge until velocities exceed 50% of light speed, and they become dramatic only beyond 90%. Crossing the gap between 20% and 90% of light speed may be the greatest challenge in all of propulsion physics. No known fuel source, energy system, or engine design can bridge that divide. The laws of physics permit it, but they demand energy on scales humanity has never approached. And yet, physics does not forbid relativistic travel. The equations allow velocities arbitrarily close to the speed of light, constrained only by the energy available for acceleration. Time dilation genuinely compresses journey times for travelers, transforming interstellar distances from impossible to merely extreme. The universe has not erected barriers to exploration. It has simply set the cost extraordinarily high. Whether humanity will ever meet that price remains unknown. The engineering challenges are immense. The energy demands exceed current capabilities by factors that defy intuition. The development timelines stretch across generations, requiring sustained commitment rarely maintained by civilizations. But the physics is clear. Given sufficient velocity, a human lifetime could span distances that light itself requires millennia or millions of years to cross. The final question, then, is not technological, but cosmic. What happens when we assume perfect propulsion? When we stop asking what technology might achieve, and instead ask what physics itself allows a human lifetime to encompass? Even with propulsion so advanced, it appears godlike. Energy at will, instantaneous acceleration, routine travel at 99.9999% of light speed, limits remain. They do not arise from engines or fuel. They emerge from the structure of the universe itself. Spacetime is not a static stage through which travelers move. It is dynamic. It expands. It stretches. Galaxies are carried apart like raisins in rising dough. This expansion creates horizons beyond which no traveler can ever go, regardless of speed or longevity. The observable universe defines our first boundary. Centered on Earth and extending about 46.5 billion light-years in every direction, it contains all the light that has had time to reach us since the beginning of cosmic history. Its full diameter spans roughly 93 billion light-years. Within this volume exist trillions of galaxies, each containing hundreds of billions of stars, each potentially hosting worlds where life may have arisen. Beyond this horizon lies a realm forever inaccessible. No telescope, no detector, no signal of any kind has ever arrived from beyond it. Not because of technological limitations, but because spacetime itself prevents it. And it is here, at the boundary of what can ever be known, that the ultimate limits of human exploration finally come into focus. In a very real sense, this spherical boundary defines everything the universe will ever reveal to us. But the observable universe is not the same as the reachable universe, and that distinction is decisive for any traveler hoping to cross cosmic distances. Light arriving at Earth today from the most distant galaxies began its journey more than 13 billion years ago, when the universe was far younger and far more compact. During that immense span of time, the fabric of space itself has stretched. Galaxies that emitted light when the universe was young now reside more than 46 billion light-years away, carried outward by cosmic expansion. And that expansion is not slowing down, it is accelerating. In 1998, two independent teams studying distant supernovae made a discovery that overturned a century of assumptions. The expansion of the universe is speeding up over time. This acceleration is driven by a mysterious component now called dark energy, which accounts for roughly 68% of the universe's total energy content. As a result, distant galaxies recede from us faster with every passing year. This revelation earned the 2011 Nobel Prize in Physics and permanently altered our understanding of cosmic destiny. Dark energy introduces a boundary even more fundamental than the observable horizon. The Hubble sphere marks the distance at which cosmic expansion matches the speed of light. At this boundary, roughly 14 billion light-years from Earth, galaxies recede at exactly 186,000 miles per second. Beyond it, recession velocities exceed the speed of light. This does not violate relativity. The galaxies themselves are not moving through space faster than light. Space is expanding, carrying them along like boats drifting apart on a swelling ocean. The distinction is technically crucial, but emotionally irrelevant to any would-be traveler. Whether motion occurs through space or because space itself is expanding, objects beyond the Hubble sphere recede faster than any spacecraft or signal can ever approach. Light emitted today from galaxies just beyond this boundary embarks on a journey with no destination. Each photon moves forward at light speed, yet the space between source and destination expands faster than the photon can cross it. These photons will travel forever, never reaching any observer, never delivering the information they carry. Entire regions of the universe are already causally disconnected from us, sealed away not by distance alone, but by the expansion of space itself. Yet even the Hubble sphere is not the final limit for travelers. Here, the difference between light and spacecraft becomes critical. A photon travels at light speed from the moment it is created. It cannot accelerate. A spacecraft, however, can continue accelerating, potentially outrunning the local expansion of space at its current position, and pushing outward into regions where Earth's light will never arrive. The true boundary is the cosmological event horizon. This horizon, currently about 16 to 17 billion light-years from Earth, defines the maximum distance any signal or traveler leaving today could ever reach, even with unlimited speed and infinite time. Beyond this boundary, cosmic expansion has already won. Space stretches faster than any approach velocity can overcome. Destinations beyond the event horizon are not merely difficult to reach. They are unreachable by any process consistent with known physics. The mathematics defining this horizon emerge from integrating the universe's expansion history forward into the infinite future. As dark energy continues to drive accelerated expansion, the event horizon does not remain fixed. It shrinks. Regions that are reachable today will eventually slip beyond it, becoming permanently inaccessible. The window for cosmic exploration is not infinite. It is closing. Current cosmological models suggest that within roughly 100 billion years, the event horizon will contract until only our local group of galaxies remains accessible. The Andromeda Galaxy, currently falling towards the Milky Way under mutual gravity, will merge with it long before this isolation becomes complete. But every other galaxy in the observable universe will vanish beyond the horizon. On even longer timescales, trillions of years, isolation becomes nearly absolute. Future astronomers living in whatever galaxy emerges from the Milky Way Andromeda merger will observe a universe containing only their immediate stellar neighborhood. No external galaxies will be visible. The cosmic microwave background, the faint afterglow of the Big Bang, will have redshifted beyond detectability. Every observational clue pointing to cosmic expansion and a hot, dense origin will have disappeared. Those future observers may never discover that other galaxies once existed at all. They might construct cosmology from first principles, observing only their local stars, and conclude that their galaxy is the entire universe. The evidence for the Big Bang, for cosmic expansion, for the trillions of galaxies we see today, will have been erased by the very expansion that carried that evidence beyond reach. This creates a cosmic countdown. Every galaxy, every star cluster, every large-scale structure we might dream of visiting has an expiration date, a moment after which it becomes permanently unreachable. The universe offers a window for exploration, and that window is narrowing. Within these constraints, how far could a single human lifetime truly extend? Answering that question requires combining time dilation with the geometry of an expanding universe, calculating not only how far a traveler can go, but how far the destination itself will move during the journey. At 99% of light speed, a traveler maintaining that velocity for 50 years of subjective time would traverse roughly 350 light years. Earth would age about 355 years during that same interval, but the traveler's biological clock would register only 5 decades. Within that radius lie tens of thousands of star systems, many host planets. Some resemble our sun, others are entirely different. Stellar nurseries where stars are actively forming, ancient globular clusters filled with stars older than the galactic disk, red dwarfs that will burn for trillions of years. Massive blue giants destined to explode as supernovae within millions. A single lifetime at 99% of light speed opens access to regions of the galaxy utterly unlike our solar neighborhood. Increase the velocity to 99.9% of light speed and the scale transforms. The gamma factor exceeds 22. 50 years of ship time corresponds to more than 1,100 years on Earth. During those 50 subjective years, the traveler would cross roughly 1,100 light years, a volume of space containing millions of star systems and perhaps billions of potentially habitable worlds. The Orion Nebula, one of the most dramatic stellar nurseries visible from Earth, lies roughly 1,300 light years away. At 99.9% of light speed, a human traveler could reach this region of glowing gas and newborn suns, observe stars igniting, watch protoplanetary disks condense into future worlds, and witness some of the most breathtaking structures in the Milky Way, all within a single lifetime. And beyond Orion, the horizon keeps expanding. Arriving after 50 years of personal aging, Earth would have advanced by more than 1,000 years. Push the velocity higher to 99.99% of light speed, and the transformation becomes even more profound. The gamma factor now exceeds 70. Within this reach lies the Carina Nebula, a vast and violent star-forming complex some 7,500 light-years distant, accessible in just over a century of shipboard time. The Eagle Nebula, home to the iconic Pillars of Creation, sits nearly 7,000 light-years away, reachable within 100 subjective years. At these velocities, even the heart of the galaxy begins to move from fantasy toward theory. Sagittarius A, the supermassive black hole anchoring the Milky Way, contains roughly 4 million times the mass of our Sun and lies about 26,000 light-years from Earth. At 99.99% of light speed, a traveler could reach this gravitational titan in approximately 370 years of ship time. A multi-generational crew departing Earth when Rome was still a fledgling republic would arrive in what feels, biologically, like a long but survivable journey, emerging amid dense star clusters and extreme astrophysical environments found nowhere else in our galaxy. Push the velocity further, and the numbers become genuinely destabilizing to intuition. At 99.999% of light speed, gamma exceeds 223. 50 years of subjective time now spans more than 11,000 light-years, nearly halfway to the galactic center. At 99.9999%, gamma climbs past 700. 50 years of personal time carries a traveler across 35,000 light-years, beyond the galactic core, and deep into the far side of the Milky Way. Consider what this implies. A single individual could, in principle, board a spacecraft, accelerate to extreme relativistic velocity, traverse the entire diameter of our galaxy, and emerge on the opposite side, nearly 100,000 light-years from Earth, having experienced the journey as roughly a century and a half of personal time. With hypothetical life extension technologies, one human consciousness could explore regions of the galaxy forever hidden from Earth-based telescopes by dust, gas, and distance. Push gamma into the thousands, and intergalactic travel enters the realm of mathematics rather than fantasy. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at about 160,000 light-years, becomes reachable at a gamma factor near 3,200. A traveler could arrive in 50 years of ship time, while Earth aged 160,000 years. The civilization that launched them would have risen, flourished, and vanished long before their arrival. Yet the traveler themselves would have aged only 5 decades. The Small Magellanic Cloud, 200,000 light-years away. The Sagittarius Dwarf Elliptical at 70,000. The Ursa Minor Dwarf at 200,000. Entire companion galaxies become accessible within extended human lifetimes at sufficiently extreme velocities. A traveler willing to spend a century in subjective transit could explore stellar populations fundamentally different from those in the Milky Way's disk. And then comes Andromeda. At 2.5 million light-years, Andromeda is the nearest major galaxy to our own. Larger, richer, and containing roughly 1 trillion stars. Reaching it demands gamma factors in the tens of thousands. At gamma equal to 50,000, 50 years of personal time corresponds precisely to the distance separating us from Andromeda. A traveler departing Earth today would arrive having aged 50 years, while Earth advanced 2.5 million. They would step into an entirely separate island universe. Unfamiliar constellations circling an alien galactic core, unimaginably distant from anything resembling home. Andromeda hosts stellar populations both older and younger than those of the Milky Way. Its central bulge is more massive. Its supermassive black hole is estimated at 100 million solar masses, roughly 25 times larger than Sagittarius A Beast. Dozens of satellite galaxies orbit it, many harboring worlds unlike any in our cosmic neighborhood. But none of these discoveries could ever be shared with Earth. Even if communication were possible, any signal would require 2.5 million years to return. The civilization that launched the traveler would be irretrievably gone. In every meaningful sense, the traveler would become a citizen of Andromeda, their journey a one-way exile into an alien cosmos. Push gamma higher still, and the scale turns cosmological. The Virgo cluster, containing more than 1,300 galaxies and lying 54 million light-years away, becomes reachable at gamma values near 180,000. A traveler would age 50 years, while Earth aged 54 million. Dinosaurs walked the planet more recently than such a departure would appear to future Earth observers. The Coma cluster at 320 million light-years. The Perseus cluster at 240 million. Entire galactic cities bound by gravity fall within theoretical reach at gamma factors in the millions. A traveler could observe the architecture of the universe on scales that telescopes can only glimpse as faint smudges of ancient light. At the absolute extreme, where gamma approaches billions, the mathematics permits journeys across most of the observable universe within a single subjective lifetime. A spacecraft accelerating at 1 Earth gravity, flipping midway to decelerate, could theoretically reach today's observable horizon in roughly 45 years of ship time. The traveler would age 45 years, while the universe aged nearly 28 billion. They would arrive at destinations we currently see only as relic light, discovering them transformed beyond recognition by cosmic time. Yet even here, physics enforces its final boundary. The cosmological event horizon cannot be crossed, no matter the velocity. Destinations beyond roughly 17 billion light-years are forever unreachable. Worse still, destinations within reach today may slip beyond the horizon during long journeys, carried away by accelerating expansion. The accessible universe contracts even as travelers race outward, and every relativistic journey carries an irreversible cost. Time dilation allows you to cross immense distances while aging slowly, but it does not allow you to return to the time you left behind. Every voyage becomes a one-way passage into the future. Consider a round trip to the Pleiades, roughly 440 light-years away. At 99% of light speed, the outward leg consumes about 445 Earth years, but only 63 years of ship time. The return doubles that. The traveler comes home having aged roughly 126 years, to an Earth nearly 9 centuries removed from their departure. Languages altered, cultures transformed, nations vanished, technologies unrecognizable. The traveler would return not as a citizen, but as a relic, a living artifact from a forgotten era. Push the journey farther, and the isolation grows absolute. A round trip to the galactic center, at 99.99% of light speed, would return a traveler to an Earth more than 500,000 years in the future. Time dilation unlocks the universe, but it seals the door behind you. Modern humans have existed for roughly 300,000 years. The Earth awaiting that traveler's return would be separated from their departure by more time than Homo sapiens has existed as a species. A hypothetical round trip to Andromeda, if accomplished at extreme relativistic velocities, would bring a traveler back to an Earth 5 million years in its future. 5 million years ago, the human lineage had not yet split from other great apes. Whatever beings walked the planet upon the traveler's return would be as distant from us as we are from Australopithecus. These numbers reveal that relativistic travel is unlike any form of movement humanity has ever known. The great voyages that shaped human history, the crossings of Columbus and Magellan, the expeditions of Lewis and Clark, the journeys of the Apollo astronauts, all preserved a thread between departure and home. Messages could be sent, memories remained shared, travelers returned to people who remembered them, distance strained relationships, but did not erase them. Relativistic journeys sever those threads completely. A traveler who leaves Earth for distant stars does not merely abandon a place, they abandon an era. They become a time traveler, moving relentlessly forward, incapable of returning to the moment they left behind. Even if they come back to the same coordinates in space, they arrive in a future that shares no cultural, biological, or historical continuity with the world they knew. This reframes the question of how far a human can travel. It becomes a choice between distance and connection, between discovery and belonging, between exploration and return. For one-way travelers willing to relinquish their past forever, the theoretical limits approach the edge of the observable universe. A lifetime measured in subjective decades could span billions of light years, carrying human consciousness to galaxies that today appear only as faint smudges in our most powerful telescopes. The laws of physics allow journeys so vast they would eclipse the grandest visions of science fiction. For travelers who hope to return, or at least remain within a civilization that might recognize them, the limits contract sharply. To come home within a few centuries of Earth time, preserving any meaningful continuity with human society, exploration is confined to perhaps a few hundred light years. Even this modest range includes hundreds of thousands of star systems and potentially billions of planets. Yet it remains a microscopic fraction of the Milky Way and an infinitesimal portion of the cosmos as a whole. The deepest implication of these calculations lies in what they reveal about humanity's place in the universe. We inhabit a cosmos that permits exploration on scales far beyond our intuitive grasp. The laws of physics do not imprison us within our solar system. They offer pathways to other stars, other galaxies, and even the vast structures that span billions of light years. The barriers we face are technological, not fundamental. They reflect our inability to command the necessary energies, not prohibitions written into nature itself. The universe has not confined biological life. It has quietly embedded loopholes, mechanisms through which consciousness could, in principle, reach the farthest observable edges of reality. A single human lifetime, measured in subjective experience, could encompass journeys that would have humbled the gods of ancient mythology. From one small planet orbiting one ordinary star in one unremarkable galaxy, a person could travel far enough to witness superclusters of galaxies, cosmic voids hundreds of millions of light years wide, and the vast filamentary web that defines the universe's large-scale structure. And yet, these same equations expose our profound isolation. Even with flawless technology, most of the universe remains forever unreachable. The cosmological event horizon retreats as we approach it, carried outward by the same expansion that defines our epoch. The overwhelming majority of galaxies we observe have already slipped beyond any possibility of contact. We see their ancient light, but we will never set foot on their worlds. The roughly 2 trillion galaxies within the observable universe form a catalogue of cosmic inaccessibility. Perhaps 1/1,000,000th of them, those within our local supercluster, might be reachable before expansion seals them away. The rest exist only as images, light that traveled billions of years to reach our telescopes, depicting places we can never go. This perspective does not diminish the significance of reaching the stars. It places that achievement in context. Humanity could become an interstellar civilization, spreading across hundreds or thousands of light years, populating worlds throughout our spiral arm, and still occupy an infinitesimal fraction of what exists. We could colonize the entire Milky Way and remain, cosmically speaking, a single grain of sand on an endless shore. Ultimately, The question of how far a human can travel in one lifetime becomes a question of what kind of journey we choose to take. Physics permits astonishing range. Engineering determines feasibility. But beyond both lies choice. Every destination implies a trade-off between distance and return, between isolation and connection, between witnessing the unknown and remaining part of a shared human story. A traveler bound for Andromeda accepts a one-way passage into an alien universe. They will never see another human face from their original era. They will never share their discoveries with the civilization that enabled their journey. In a very real sense, they become the seed of a new human branch, planted in foreign cosmic soil, severed from the tree that produced them. Perhaps some would find meaning in that sacrifice. Perhaps knowing that human awareness had escaped its home galaxy would justify everything left behind. Perhaps standing beneath Andromeda's trillion stars would outweigh the cost of exile. Or perhaps the human spirit values connection more than distance. Perhaps the most meaningful journeys are those that allow return, that preserve the fragile threads linking explorers to home, memory, and shared discovery. There is no single answer. Some will push outward toward the event horizon, chasing the farthest reach of human consciousness. Others will explore closer to home, balancing wonder with belonging, range with return. The universe is indifferent to the choice. It offers the same laws to every traveler, the same time dilation at every velocity, the same expansion in every direction. What we ultimately do with those cosmic conditions is a decision no equation can make for us. You live in a universe nearly 93 billion light-years across, a universe shaped by structures so vast that light itself needs billions of years to cross them. From one small planet orbiting an ordinary star, you look outward at distances that demand numbers with dozens of digits just to be written down. This scale does not simply exceed human experience. It exceeds human intuition. And yet, within the span of a single lifetime, given technologies we can envision, but have not yet learned to construct, a human being could, in principle, traverse meaningful portions of that incomprehensible immensity. The universe has not surrounded humanity with walls. It has laid out corridors extending toward every horizon. Corridors we do not yet know how to travel, but that physics itself declares passable to anyone capable of reaching the required speeds. So how far could one human truly go in a lifetime? The answer does not reside in mathematics alone. It depends on what we are willing to build, what we are willing to sacrifice, and what we are willing to sustain across generations. It depends on whether we value distance over return, exploration over continuity, discovery over belonging. These are not physical constraints, they are human ones. The stars are not unreachable, they are patient. The galaxies are not forbidden, they merely demand velocity, and a willingness to accept the time that velocity extracts in return. Embedded within the equations of motion through space-time is a quiet promise. Distances measured in millions of light-years could someday fall within the scope of a single human life. That promise is not speculative fantasy. It is written into relativity itself, confirmed by a century of experiment, and waiting only for engineering capable of turning mathematical permission into physical reality. The universe does not resist exploration. It invites it. Somewhere between the 430,000 miles per hour we have already achieved, and the velocities where gamma climbs into the millions, lies a threshold. A point where human exploration of the cosmos shifts from imagination to inevitability. The ultimate limit on how far a human can travel in one lifetime is not imposed by physics. It is imposed by our ambition, our resolve, and our willingness to pay the price the universe demands for passage beyond home. The roads are there. We have simply not yet learned how to walk them.